Okay, let's go over an example. So, say you've been tested for COVID-19 and your doctor confirms that you have tested positive. Our question today is this: what is the probability that there's been a mistake in your test results? So you do some research and you find out that the COVID test is 80% accurate. So what exactly does this mean? A test accuracy is a combination or a mean, a statistical average of the test sensitivity and its specificity. So sensitivity is the probability that you test positive if you do have the disease. So what that means is that if you actually have COVID, you want your test to come back positive. You want to get that true positive result that says, yes, you are sick. We did find COVID in your test result. Specificity is the probability that you test negative if you do not have the disease. So if you're healthy, you don't have COVID, you want your test to come back negative. So just note that both of these go with the correct test result, right? So sensitivity is the probability that you test positive if you do have the disease. Specificity is that you test negative if you don't have the disease. So it's two different kinds of accuracy. So our total test accuracy is going to be those two added together and divided by 2. So if you do research, you'll find that the COVID swab testing has a sensitivity of 90% and a specificity of 70%. So let's break that down a little bit more. Let's say that OU gets funding to test every single person that's on the OU campus. So OU has about 40,000 people on campus between staff, faculty, and students. So right now, COVID has about a prevalence rate of about 3%. So what that means is of those 40,000 people who are at OU, we would expect about 3% of them to actually be sick. So if we take 40,000, we multiply it by 0.03, we would expect about 1,200 people to be sick. So we're going to put that right here in our sick total. That means our healthy total is going to be everyone except for the people who we would expect to be sick. So we're going to take 40,000 and subtract that 1,200 to get 38,800 healthy people at OU. So now let's think about our test results and their accuracy. So first we have a sensitivity of 90%. So what that means is that of the people who are actually sick, so of our 1,200 people who are actually sick, our test is going to catch 90% of those cases. So if we test all 1,200 people, we would expect to see 1,080 positive results. So those are true positive, real sick people who actually tested sick. But we're still going to get some false negatives. So our test isn't 100% accurate, right, in this area. So we would expect some people who are actually sick to still get those negative test results. We would see 120 of those sick people get negative results, so inaccurate results. Now, if we look at our specificity, we'll see that our specificity is 70% accurate. So of the 38,800 healthy people that we have at OU, if we tested all of those people, we would expect to get the correct result for 70% of those tests. So what that means is of those 38,800 healthy people, we would expect to see 27,160 true negatives. So accurate negative tests where healthy people are testing negative. But we're going to see a lot more false positives. So false positive is when you're actually healthy, but you're testing as if you are sick. So with a specificity of 70%, we would expect 30% of our people who are healthy to actually get positive test results. So we would expect 11,640 false positives. So if we look at this all together, if we tested everyone on campus, we would expect to see about 12,720 people to test positive. Of those, 1,080 would actually have COVID. And that means we're going to have a decent amount of people who are going to test positive for COVID, but not actually have it, and hopefully not get too many people who have COVID and have that false negative. So in some way, this is a little bit of good news, right? So there's a 91.5% false positive rate for the disease using our current technology. So there is a chance that you might not have COVID after all, even if you do test positive. Now, does this mean that you should hit campus corner, right? So you can't get that positive COVID test and say, okay, well, there's a 91% chance that I'm not actually sick, right? We have to think about why it's important to have this higher sensitivity than it is to have the higher specificity. So let's ask ourselves, why is it more important, again, to have that high sensitivity versus that high specificity? So what happens when a false positive stays home and quarantines, right? So if you get a false positive, you have that positive test even though you're not sick, the worst thing that's going to happen is that you're going to have to stay in your dorm, you're going to have to stay in your house for those 2 weeks and hopefully not come into contact with anyone else, right? So although you might be bored, it's not always fun to sit at home, the worst thing that's going to happen is that you have to quarantine for a little bit, right? But what happens if you get that false negative? So if you're actually sick and your test comes back and says that you don't have COVID when you actually do, right? So we don't want those people to be going out in public, unknowingly spreading the disease, especially if they're asymptomatic. So it's really, really more important to make sure that we're minimizing those false negatives, not as much as of an importance to make sure that we're minimizing those false positives, right? Because we think about it, there's a low risk of negative outcomes if a healthy person stays at home for 2 weeks, but there's a really, really high risk of negative outcomes if that sick person isn't identified. Okay, now that we covered our different types of statistical tests, I want to go over a few examples using some real-world data. So first, we're going to talk about our chi-square test of independence. So remember, we use our chi-square test when we're trying to determine whether or not there's a relationship between two categorical variables. So categorical variables, as a reminder, means that you're just in one category or the other. You can't be in more than one. So critical values can be found using a chi-square chart, and p-values are going to be found using our statistical software. So again, chi-square tests are going to allow us to assess whether there's a meaningful relationship between two variables, as opposed to just a chance random relationship. So our null hypothesis is going to be that there's no relationship between our variables, which makes our alternative hypothesis that there is some sort of relationship between those two categorical variables. So our formula for chi-square is going to look like this. Our O is going to stand for observed, and E stands for expected. So we take our observed, we subtract our expected, we're going to square all those values and divide by its own expected value. Then with that sigma, that means we're going to add all those values up. So again, I'm going to show you an example using real world data, because that's where our observed values are going to come from. So our observed values are what we actually see. So that real data that we collect from our sample, those are going to act as our observed values. Our expected values is going to be something that we calculate based on what we would expect to see if there's absolutely no relationship between those two variables. So the way that we calculate our expected values is by taking our row total, multiplying it by our column total, and then dividing it by our table total. So let me show you using, again, some real world data. So this is COVID data collected by the state of Oklahoma and published online. So far, we've had 98,621 cases of COVID-19 in Oklahoma. Of those, 1,095 people have died. So we can look at the relationship between COVID mortality and age, right? So if we expect to see some sort of relationship between age and COVID, we should expect to see different people dying at different rates depending on whether or not they're over 65 or under 65. So our first step to do our chi-square test is going to be to calculate our expected values. So again, you're going to take that row total times the column total divided by the table total. So for this first category, for people who are under 65 who have died of COVID, we're going to go across, take our row total, 84,956. We're going to multiply it by our column total, so 1,095, and then divide it by our table total of 98,621. Then we get this expected value of 943. We're going to go through and do this 3 more times, right? So we have an expected value for each possible cell in our table. From there, we can start plugging things into our formula. So I copied over our observed and our expected values. We're going to subtract our expected from the observed. We're going to square those to make sure that we get rid of those negative numbers. And then we're going to divide each value by its own expected value. So even though this column, all the numbers are exactly the same, you can see this column, they change, right? Because I am going to divide by the numbers in this second column right here. So each one should be a little bit different. From there, we're going to sum all of those up This gives us our chi-square value, which is what we're going to compare to our critical value. So our critical value for this question is 3.84. Since 3.84 is significantly less than 4,094.3, we're going to reject that null that there is no relationship. And we're going to conclude that there is a relationship between age and COVID mortality, with people at 65 or older being at a greater risk of dying from COVID than people who are under 65.